Tutors. Today we'll still focus on the course Physics 124, Geometric and Wave Optics. Unit 3 of this course is Refraction at Plane Surfaces. And the objective we are going to be looking at today is the bending of ray of light when it travels from air to water. The bending of ray of light when it travels from water to air, laws of refraction, Snell's law, refractive index, critical angle, and total internal reflection. We'll also look at the application of total internal reflection. So sit tight and enjoy the course. Make sure you stay tuned to the end so that you can get the full objective, everything that is mentioned in the objectives. And if you're not subscribed to our channel, please subscribe to our channel to get more content. Alright, so we'll dive in. So we have reflection or refraction at plane surfaces as the topic. You know, we talked about reflection. What's the difference? Reflection is when you have a plane surface that is polished at one end, and we saw that incident ray on it will generate reflected ray. So reflection occurs when incident ray on the polished surface result to ray bouncing back. Ray is bouncing back. So this is for reflection. Now refraction happens when the material, the surface, is transparent. It's transparent. It's not coated at one end. It's transparent. So we're looking at objects coming in, ray coming in into the object and still going out of the object. But in this case, the ray of light will not continue in a straight line. Why? Because the material medium is a different material medium. For instance, if the ray of incident ray is coming in from this part, and you have air medium at this part, and at the second part you have maybe water medium. Now agree with me that these two mediums are different density. This one, the speed of light here in the air medium is will be faster than the speed of light in the denser medium. So the air medium is less dense medium, and the other medium, water medium, is more dense medium. So the density here is more. So the speed of light is altered when it enters here. So what happens is that when light ray hits this place, it changes direction. Instead of it to go continuous the way it is like this, it bends slightly away from its direction. There exists a point called the normal. The normal is a point. The point is arbitrary. It's not real to us. We just put it there for purpose of analysis. The normal is perpendicular to this point where the incident ray bends when it encounters this medium. So there's an angle formed between this incident ray and the normal. The angle is called the angle of incidence, and the angle between the refracted ray and the normal again is called the angle of refraction. Okay, so I will make both to say that this ray into this medium is called the incident ray, and this one on the other side of the medium is called the refracted. So we are talking about refraction this time, refracted ray. So there's an angle of incidence and there's an angle of refraction. Okay, so this is the basic story behind refraction. Note that we are talking about two mediums. One is denser than the other. Okay, so the denser one will cause the ray of light to bend towards the normal, and the less dense one, the ray of light is more away from the normal than the denser medium. Okay, so we'll look at the laws of refraction. The laws of refraction. The law of refraction, there are two things we need to know here. That the ray of light the ray of light coming in into the into this medium, and the reflected ray and the incident all lie on the same plane, and the angle of incidence, there's a ratio that exists. There's a ratio that exists between the sine of the angle of incidence and sine of the angle of refraction. That ratio is called N. That ratio is called N. That is the refractive index. N is equal to refractive index. So it's a constant. It's a constant. Refractive index. N is the refractive index. It's a constant. So most of the time we ask to calculate the refractive index given the angle of incidence and the angle of refraction. Sorry. Okay, so on the board is the statement of Snell's law. So there are two statements here for Snell's law. The angle of the incident ray, reflected ray, and normal at the point of incidence all lie on the same plane. So this looks similar to the laws of reflection. So this is refraction, Snell's law. Now, second point in Snell's law says that the ratio of the sine of angle of incidence to the sine of angle of refraction is a constant for two media. So this is the mathematical expression for that ratio of sine of incidence to sine of refraction. Okay, so note this because we're going to be using it to do a lot of solving. Refractive index. So you see that the speed of light is different for different substances like air, sand, water, and glass. Speed of light varies for this media. So let us consider that the speed of light in a vacuum or air is c, for instance, and the speed of light in some other substance is v, like water. Therefore, the relationship between c and v, c being the speed of light in air and v being the speed of light in a denser medium, can also be denoted as refractive index. So we've talked about this one. Then we can also talk about speed. So let me take this one off. And now I'll also tell us that with speed, we can also get refractive index. So from Snell's law, we know that mathematically, N is equals to sine I over sine R. And also, N can be speed of light in air over speed of light in another medium. So we are comparing two mediums, air and another medium. So air is up there and another medium. So this other medium can be glass, can be water, and what have you. So you see that the ratio between the speed of light in one medium and speed of light in another medium can also give us refractive index like this second case. So I'm going to give us some examples quickly so that we can apply these formulas. Okay. So we have on the board, determine the speed of yellow light with wavelength 589 nanometer in diamond. The refractive index of diamond is 2.42. Take speed of light to be 3 times 10 to the power 8 meters per second. Okay, so refractive index in terms of speed of light and speed of material is speed of light. Let me say speed of light c. Let me use on c over small v. This v is not velocity here. Where c? Always define your parameters. It's equals to speed of light in air. And small v is speed of light in diamond. Already we are comparing speed of light in air to that of diamond, and the ratio of the two will give us the refractive index. So of diamond, you know, because the light is coming from the air to the diamond. Okay, so N is already given as 2.42 and C is given as 3 times 10 to the power 8. We are looking for V. note that we're not even using this nanometer. This is what we call wavelength. And you know the relationship between wavelength and speed is V is equals to F lambda. Okay, so this is what we're looking at. We're looking at V, not lambda or frequency. I'll tell you the relationship between them later, but let's just continue what we're doing here. So V is what we're looking for. So making V the formula, V is now equals to 3 times 10 to the power 8 all over 2.42. So the speed, by the time you compute this, the speed will give us approximately 1.24 times 10 to the power 8 meter per second. So the speed of yellow light, 589 nanometer in diameter, is approximately this is the speed, approximately that. So that's fair enough. I'm going to give us another example. Okay, so we have on the board a question. It says a beam of light of wavelength 550 nanometer traveling in air is incident on a surface of transparent material. The incident beam makes an angle of 60 degrees to the normal, and the refracted beam makes an angle of 45 degrees to the normal. Calculate the refractive index of the material. Okay, it also will pay us to just do a visual on this. Let me just try to visualize this. This is the two different material. This is the medium, this is the normal. So we said that the beam of light is of wavelength is incident on this. This is the normal. This is 60 degree incident ray, and the normal continues like this, of course. Then the refracted ray is what, 45 degree. And note something that we said before. You see, because this, let me put this 45 degree first. Okay, 45 degree. And because this is a beam of light traveling in air, so this medium is air. Here is air, and this side is air, and this other side is transparent material. It's a transparent material. So, of course, this material has more density than air. So you see that the laws of Snell's law is obeyed. That the incident ray is as it enters here as refracted, it bends towards the normal. So the angle that this refracted ray is forming with the normal is smaller than the angle that the refracted incident ray is forming with the normal. So it shows that, okay, this is in line with what we have said before. But we are now told to calculate the refractive index of the material. Now we are also given from Snell's law, the second formula, that the ratio of angle of incidence, the ratio of the refractive index of the two material is equals to the ratio of their signs of incidence. Signs of incidence. Okay, so let me say this is a sign of incident here, and sign of angle of incidence and sign of angle of refraction. Yes. All right. Okay, so this is in line with Snell's law, line of Snell's law. So I can come and define it where Ni or N1, not I, is the refractive index in the first medium. Refractive index in air. Let me call it air. N2 is refractive index in water. Sorry, in material, not water. In material. Okay, so I is incident angle and R is refracted angle. I is incident angle, and R is refracted angle. Okay, so this one now can be put in this formula. Incident. Okay, so we're looking for, what are we looking for? We're looking for the refractive index of the material. Okay, so the material. Okay, so do we have refractive index of the light in air? Okay. The incident beam makes an angle of 60 degrees. Normal refracted beam. Okay, so the refractive index for air is 1. It's 1. Okay, so it's 1. It's 1. Always. Air is 1. So I'm writing this formula again. I'll say 1 over material is what we're looking for, N2. Sine of incident is 60 degree. Sine of angle reflected is 45 degree. So at this point, we've just gotten, it's just to look for N. Okay, so I'll just wrap up at this point, at this side. Okay, so we know that the sine of 60 degree is 0.866. So I can just come here and say N2 is equals to, of course, 1 times sine 45 over sine 60. Yeah. Okay, so N2 is equals to sine 45 is what's sine 45? Let's sketch 45 sine 60. Hold up, let me complete it quickly. Okay, I just saw a mistake from our formula. Snell's law for comparing two material medium is N1 sine I is equals to N2 sine R. Okay, so the two, we are comparing the refractive index of air, where N1 is refractive of air, comparing it to the incident angle on air, via air, and the refractive index of the material and the refracted angle. Okay, so if you have this diagram illustration again, okay, so this is normal, this is I, and this is refracted angle. So this is the air, and this is the material. Okay, so you are comparing the refractive index N of air to the sine of incident in air. To the refractive index in material over sine of refraction on material. So the two parameters are on the same side and the other side as well. So what we have here for air, this is air side, this is material side. For air, index is 1. Sine of incidence here is sine 60. Understand? And for material is 2. Sine of refraction is 45. Okay, so this one is now easy enough. We actually missed our way, but we have gotten it back again. So we're looking for N2. So 1 times sine 60 over sine 45. That is if you make N2 solution formula. That is this N2 here. This N2 here. Okay, so what is sine 60? Sine 60 will give you 0.877. If you compute that, 0.866. Sine 60 will give you 0.866. So I have 0.866 all over sine 45. Sine 45 will 0.707. That is N2. N2 is the refractive index in the other side, in the material. So finally, N2 will be approximately 1.77. But it does not have any unit. So that's the answer for that, 1.22. 1.22. Thank you for that. 1.22. Okay, so that is for that question. So we'll move into a concept known as critical angle, and then we'll wrap it up with total internal reflection. Critical angle. Critical angle. So we said that for refraction, that if you have the material like this, or have one material like this, so for critical angle, we said that when there is two material, we are looking at maybe water this way, and we have air this way. You know that air is the less dense material. Less dense. What happened to the less dense material? The angle between the incident ray or refracted ray is bending away from the normal, and for water, which is the denser material, the angle is bending towards the normal, denser material. Okay, so you know we have been looking at cases where the incident ray comes from the less dense material. The speed of light is faster, there and they're slower in the denser material. But what if there is this is normal. What if the angle of incidence is coming from this denser material? Okay, so let's say this is water and the angle of incidence is coming like this. Understand? So for each angle of incidence, the reflected ray is bending towards the number. Sorry, away from the number. Away. So I have incident ray like this and refracted ray like this, because we are doing it the other way around. So the angle of incidence from the denser medium is refracted in the less dense medium. So the angle of refraction is bending away from the normal. So the angle of refraction is more than the angle of incidence. The refractive index in this case should be less than 1. Always less than 1. You see all this I'm making now? It's just deduction, so that when you are reasoning some questions, you should know what you should be expecting. If I'm looking from a denser material to a less denser material, my refractive index should not be more than 1. Why? Because already my angle of incidence is smaller than the angle of refraction. Why? Because the angle of refraction, the angle is bigger because the refracted ray is bending away from the normal. Okay, so this is what we have. Now, even if we start to increase it, we do another one, and we increase this angle of incidence again. You see that the angle of refraction will also still bend further away. So, if we also increase to another point, a time will come when there will be an angle of incidence that you have the angle of refraction grazing through this horizontal, that is grazing on the surface of the denser medium. That means the angle of refraction at that point will be 90 degrees. This angle of incidence. So there comes an angle of incidence where the angle of refraction is 90 degrees. That angle of incidence where the angle of refraction is 90 degrees is called the critical angle. So I will call it theta C. Theta C is the critical angle, and is defined as the angle of incidence, as light travels can't spell travel again. What's one? Oh my word. Travels. Okay, as light travels from a denser medium to a less dense medium, where the angle of refraction is 90 degrees. Okay, so critical angle theta C is the angle of incidence as light travels from denser medium to from a denser medium to a less dense medium, where the angle of refraction is 90 degrees. So at this point, refractive index is equals to sine theta C over sine 90. It's always, the bottom is always sine 90. And if that's the case, sine 90 is always 1. So n is equals to sine theta C. So the refractive index at critical angle is sine critical angle, because there's no denominator at that point. Now, that is critical angle. But if we still, as we are moving this angle of incidence, if we now move it beyond critical angle, you see the levels. I have incident 1, incident 2, incident 3. Incident 3 is the critical incident. And incident 4, incident 3, when the incident 3 is at position 4, there's what they call total internal reflection. Now, the refraction, angle of refraction will now be more. There's no angle of refraction actually, because the principle is that as the angle of incidence is increasing, You understand? The angle of refraction also increasing more. Why? Because the angle of refraction bends further away from the normal. So it's bending this way. As you are increasing the incident angle, your refracted angle is bending this way. A point will come when you bend it, it will now be 90 degrees. That is the point where you don't have, that's the point where you have the highest angle of refraction. If you dare increase the angle of incident more than that critical angle, you will just have total internal reflection. You will not have any refraction again. It's not occurring. What is happening is total internal reflection, no refraction. Now, this is what happens when we are studying interactions between light between denser objects or material to a less denser material. So, what now happens? What now happens if what are the practical applications of total internal reflection? We know that this thing is actually seen in where you have objects underwater and they are trying to view what is above the water. So that is like for a fish under the water. How does the fish see objects above the water? This actually explains it. Now, for total internal reflection, it occurs only when light strikes a boundary where the medium beyond is optically have a lower refractive index. Okay, so there are many applications like I'm trying to bring out here. One, it is used in many optical instruments like binoculars. Okay, the principle behind the fiber optics is the total internal reflection. Through fiber optics, light can be transmitted, with almost no loss. A bundle of such light fibers is called light pipe, which can be used in human body, in medicines, and communication signals. So another application is found in optical fibers, revolutionizing the present era of telecommunications. Nowadays, optical fibers are used in place of copper cables in telecoms. They can carry a much greater number of telephone lines, like telephone calls, compared to copper cables or even microwave. Okay, so images can be transferred from one point to another easily through total internal reflection. In surgery, these fiber optic devices are very helpful to locate areas in the body which cannot be accessible in examining internal organs of the body. Okay, so finally, total internal reflection is seen in submarine periscopes. Okay, so we are concluding by saying that light rays travels from one medium to another medium, air for instance, and to another medium, water or glass, through a transparent surface. So the ray that is bent, the ray is bent actually at the surface. This bending of ray of light is called refraction, as against reflection when we see the medium being coated. So, but once it's a transparent surface, there is a bend. Why? Because the speed of light varies for the different medium. The angle formed by the incident ray of light with the normal is called the incident angle or angle of incidence, and the angle formed by the refracted ray with the normal is known as the refracted angle or angle of refraction. So the incident ray, the refracted ray, and normal at the point of incidence all lie at the same plane. That's the first component of Snell's law. And according to Snell's law, the ratio of the signs of incidence and the sign of the angle of refraction is a constant known as the refractive index for that given medium. So Snell's law can also be represented by comparing the ratio of the two mediums. Remember I said that if you have sign of incidence over sign of refraction, it's also the same thing as the refractive index of the medium where the incident occur, let me say air, and the refractive index of where the refraction occur, let me say water. So these are what we covered in this topic today, Unit 3. I hope you found this video very interesting. Kindly like and subscribe to our channel to get more content. Thank you for viewing.